In this section, we will cover interleaving for combating fading when combined with forward error correction coding. Here we have the block diagram of the OFDM transmitter and the block diagram of the OFDM receiver. We covered the forward error correction coding techniques, which are, in the case of 802.11a, using a convolutional encoder in the transmitter and a Viterbi decoder at the receiver. We mentioned that using convolutional encoder and a Viterbi decoder, the FEC is quite capable of correcting random bit errors. However, it is not very good at correcting bursty errors. Here we are adding to the path the interleaver. Let's skip over the puncture. We'll discuss that next. But we add a block called an interleaver, and at the receiver we have another block called the deinterleaver. The combination of the interleaver and deinterleaver is of course a reverse process, so that the original bit stream that is input to the interleaver is output at the deinterleaver. The purpose of the interleaver is to work on an OFDM symbol such that adjacent bits are not associated with a single carrier. The bits are actually permuted such that if a carrier is wiped out or received with a low SNR, and those bits are corrupted or some of them are in error, then those bits would actually be permuted across the OFDM symbol such that when the deinterleaver process is performed, the input to the Viterbi decoder would basically see random errors instead of bursty errors. As a background to the interleaving process and why it is necessary, here we show the spectrum, the complex spectrum of a fading multipath channel with a RMS delay spread of 150 nanoseconds, and the sampling rate is 20 megahertz, as is the bandwidth. We're showing the complex spectrum. At a RMS delay spread of 150 nanoseconds, we see that there are quite a number of fades, and at a particular carrier the fade could be quite large, and that would result in the loss of that carrier. And when that carrier is gone or damaged or eliminated, then the bits associated with that carrier are in error, and if these bits turn out to be adjacent bits, then we have a case of a bursty error. The job of the interleaver and deinterleaver is to make sure that adjacent bits are scattered among the carriers such that when a carrier is eliminated or we have errors due to the deep fade of a carrier, that the actual bits are randomized so that the Viterbi decoder can correct the random errors instead of dealing with bursty errors. Let's review the generation of an OFDM symbol, in this case for 16QAM. Here we have a data source which generates bits at a rate of R sub b, R bits per second. The bits are input to a scrambler which randomizes the bits. The bits are then input to a convolutional encoder, in this case, for example, a half-rate encoder. The convolutional encoder adds redundancy to the information bits such that at the receiver a Viterbi decoder can use the redundancy in the bits to actually correct for errors introduced by the channel and the decoding process. The bit rate at the output of the convolutional encoder for a half-rate encoder is twice the bit rate of the input information bit stream. Here we show a sequence of bits at the output of the convolutional encoder. They are input to a mapper, in the case of 16QAM. Each constellation point represents 4 bits, so we have 2 to the 4 equals 16 possible constellation points. The symbol rate for each point in the constellation is 1/4 the rate of the output of the convolutional encoder and represents a complex number. To form an OFDM symbol, recall that we group 48 carriers, each carrier containing 4 bits of encoded data, And with the 48 carriers, we add, of course, pilots and guard interval and a 0 or null at DC to form 64 carriers, after which we compute the inverse FFT and the OFDM symbol in a time domain, add the cyclic prefix and so forth, and send and transmit the OFDM symbol to the receiver through the multipath fading channel. So here we show the carriers X0 through X47, and also indicating that each carrier represents a complex number. A key point is that each carrier contains 4 bits of information because it represents a point in the constellation. And we have 48 data carriers, so each OFDM symbol, which contains 48 data carriers, contains 192 bits. That is 4 times 48 carriers equals 192 bits. So this is designated as N sub CBPS, which is a number of coded bits per symbol, per OFDM symbol. So each OFDM symbol at the output of the inverse FFT contains 192 bits of coded bits. Of course, these are from the bits of the output of the convolutional encoder. So as we show over here, every 4-bit represents a carrier. So every carrier contains 4 bits of coded bits. Here we're showing the kth bit. So we have k basically from 0 to 191, indexes through the OFDM symbol, the number of the coded bits through the OFDM symbol. So every carrier contains 4 bits in this case. Now, the process of interleaving is to make sure that each carrier that contains bits does not contain adjacent bits, so that if we lose a carrier due to deep fades and we lose 4 bits, those bits are not continuous bits within the coded bit stream. In that case, we will have a burst error, and as we mentioned, the Viterbi decoder is not very good at correcting bursty error. It is very good at correcting random bit errors. So the block that we're dealing with, that we have to correct the data for example, is containing these 192 bits for the case of 16QAM. To illustrate the interleaver and deinterleaver operation, it is best to look at this diagram. So above, we actually show the output of the convolutional encoder grouped into 4 bits each, and each associated with a carrier. And we have 192 of these bits within the OFDM symbol. Over here we show the actual bits, for example, for X0, and have color-coded them as red. And similarly, another 4 bits color-coded in green, and also 4 bits color-coded in blue, and also violet. Now, the operation of interleaving is to take these bits and, through a permutation operation, map them to different locations in the overall OFDM symbol. That is, if you consider that the OFDM symbol has 192 bits, so we take the first 4 bits and permute them within the 192 bits, and the permutation for the first 4 bits is shown here, where we have the color red, the bits shown in color red. So these 4 bits have been permuted so that they're scattered across the 192 bits in this fashion. Similarly, for this case here, where we have 4 bits associated with a carrier, and instead of associating these with a carrier, we first permute them through the interleaver, so the green bits are shown actually, again, placed further away from each other. Continuing that with the 4 bits shown here and here, we obtain the diagram in the middle, and these are the permuted bits that are then mapped to the carriers. That is, we take the 4 bits over here and map them to the constellation point, and every constellation point then is associated, of course, with a carrier. So if we look at this situation here, so this carrier, which has 4 bits of coded bits associated with it, if it was transmitted through a fading multipath channel and happened to be in a deep fade, and for example we lost this carrier, then in the de-interleaving procedure, which is the reverse of the interleaving, the bits associated with this carrier would then appear as in the locations of the original locations prior to interleaving. So this bit would appear over here, and the green bit would appear here, and the blue bit, and so forth. The point is that if this carrier was eliminated due to a deep fade, for example, then the bits associated with this loss of this carrier are in random locations, so that the Viterbi decoder will receive bit errors in these locations, which, as far as the Viterbi decoder are concerned, are in random locations. They are not adjacent to each other, like in this case. If the carriers, if we did not do interleaving, and for example a carrier here was lost, then all 4 adjacent bits would be lost. In the case of interleaving, if this carrier is lost, then the bits that are gone or in error or potentially in error have been distributed across the 192 bits of the OFDM symbol, and as they are input into the Viterbi decoder are like random bit errors, and of course the Viterbi decoder is quite capable of correcting most of those situations. So this is the concept behind the interleaving, is to take bits that are adjacent to each other, perform a permutation of those bits in such a manner that each carrier does not contain adjacent bits, as are shown in this color scheme here. And in the de-interleaving process, the bits are of course returned to their original positions, and if the carrier is eliminated, then the bits are not adjacent and are randomly distributed within the 192 bits of the OFDM symbol. The interleaving scheme proposed by 802.11a actually is a 2-step process. The block interleaver uses a block size corresponding to the number of bits in a single OFDM symbol. As we indicated, for example, for the 16QAM case, the number of bits per OFDM symbol was 192, which was of course 4 bits per carrier, and we have 48 carriers. We perform a 2-step permutation. The first permutation ensures that the adjacent coded bits are mapped onto non-adjacent subcarriers. And the second permutation ensures that adjacent coded bits are mapped alternatively onto less and more significant bits of the constellation, and therefore long runs of low reliability LSB bits are avoided. If you go back to the constellation, basically you want cases where you actually not only do permutations among the carriers, the bits that are allocated to the carriers, but you also want the bits to move around within the constellation so that you don't have a long run of bits which, for example, use the LSB part of the code bits. And here we're showing the operation of the first permutation, in which adjacent bits are allocated to carriers that are not adjacent to each other, and of course the de-interleaver causes those bits to return to their original location so that they can be decoded by the Viterbi decoder. The first permutation operation is expressed by this expression here, where we have k, which goes from 0 to, for example, in the case of 16QAM, 192, from 0 to 191, so we have 192 bits. And for each value of k, you compute an index I, which is a permutation. For example, for 16QAM, where we have 192 bits per OFDM symbol, then n sub the number of coded bits per symbol is equal to 192, and if we divide 192 by 16, we get 12. So for every index k, for example, starting from 1, each index I would be separated by 12 bits. And this achieves the permutation such that a number of things are accomplished. One is each carrier does not carry adjacent bits, and adjacent carriers also do not carry adjacent bits. The second permutation is shown over here, and we won't go into too much detail here. The best thing to do is actually show you some of the results of actually computing these indexes, and we'll get back to that. So here we're showing the index k, which goes from 0 to 191. We're skipping some of the steps. For each index k, we compute an index I, which is a permutation index, for the first permutation. As k goes from 0, 1, 2, 3, we see that the index I goes from 0, 12, 24 to 36. And therefore, the carrier associated with the first 4 bits here will have bits in locations 0, 12, 24, and 36, obviously separated by a distance and not adjacent to each other. Similarly, for the case where we have for bits 4, 5, and 6, we see we get the index I 48, 60, 72, 84, obviously the bits being selected so they are again not adjacent to each other and permuted. In the case of J indicates the index for the second permutation. We see that within the first four indexes of I, we still get another permutation where notice that bit location 12 is now 13, and bit location 36, for example, is 37. 12 itself has been moved down to a further distance away, like at position number 17. Of course, as was mentioned, the purpose of the second permutation is to avoid long runs of low reliability bits. So here we go again to this diagram. The first permutation basically achieved the case where each adjacent bits are then permuted across the 192 bits, and such that within a carrier the bits are not adjacent, and within adjacent carriers also non-adjacent bits exist. This avoids bursty errors, and in the case of any fades, where for example a number of carriers are affected, then even the adjacent carriers don't carry adjacent bits, and in the de-interleaver process the bits are then randomly moved around in terms of the 192 bits that are presented to the Viterbi decoder, and the Viterbi decoder obviously can handle random bits more effectively than bursty errors. Here we show a multipath fading channel with a 150 nanosecond RMS delay spread at 20 megahertz bandwidth. The fading characteristic shows that in some situations you have multiple carriers that are affected by the fade, and therefore multiple carriers can be damaged, and the resulting decoded bits, of course, if these bits were adjacent and mapped to adjacent carriers, then of course we'd have a big bursty error at this point. So the permutation in the interleaving process not only permutes the bits that appear within the carrier so that they are non-adjacent, but the bits between carriers are also non-adjacent between adjacent carriers. And let's show that over here. In this column here we're showing the results of the first permutation within the 192 bits of the OFDM symbol with 16 QAM. So the first permutation, the bit location 0 is mapped to 0, and of course bit location 1 is mapped to 12, bit location 2 is mapped to 24, and of course 36, and so forth. Obviously the bits within the first this carrier here are permuted such that they are not adjacent to each other. They are separated at least by 12 bits. If we go to the next carrier, we also see that within the carrier the bits are non-adjacent to each other and separated by at least 12 bits. An important point is that between the adjacent carriers themselves, the bits are also non-adjacent and are considerable distance from each other. We see this in the case of these three carriers over here, where within the carriers, of course, we have non-adjacent bits, and between the adjacent carriers we have non-adjacent bits. None of these bits are adjacent to the bits in this carrier, for example. And this is the basic operation of the interleaver, such that it permutes the bits in such a way such that within the carrier the bits are non-adjacent, and between adjacent carriers the bits are not adjacent, so that when you have deep fades you will not encounter a bursty error as far as the data that is presented to the Viterbi decoder. As we mentioned, the Viterbi decoder would correct random bit errors very effectively, but not bursty errors. And although in this presentation we refer to the interleaver sometimes as creating a condition where bursty errors appear as random errors to the Viterbi decoder, they're actually not random, but permuted. But as far as the Viterbi decoder is concerned, they might as well just be random bit error locations. It is a combination of convolutional encoding and the Viterbi decoder operation, which combined with an interleaver gives us robust and reliable communications over wireless communication links, in this case for 802.11a.